Recording is rolling. It is Friday the 13th of September. And I'm looking at the gray tray. Looks like a lot of you guys have already turned in these projectile puzzles right here. Remember, the only ones I'm going to be scoring over the weekend are these first two scenarios on the left, these two scenarios up here on the right side, and then on the back side, just the left puzzle, just that one. Okay. All right, so that's all I'm scoring over the weekend. A bunch of guys just turned that in. All right. Next on the agenda, I want to help you guys out with, yesterday I handed you guys a take-home quiz, which is going to be due when? Guys, when's your quiz due? Monday. So you guys got a few days for this take-home quiz. Right, and the first question involves a cannon blasts a cannonball, and I wanted you guys to draw some graphs: height versus time, vertical component of velocity versus time, horizontal component of velocity versus time. Since this is the long class today, I'm actually going to do two different quizzes here. I got honors and I got conceptual. Let's start with honors. Okay, this is a little bit different questions. So the honors one says, a cannon blasts a cannonball 30 degrees above the horizontal on a long flat plane. Okay, so it's one of these long flat plane situations. Draw height versus time, vertical component of velocity versus time, and horizontal component of velocity versus time. Now, I'm not going to do all of those with you, but at least I'll do some of it with you guys. Do some of it. Okay. So here on this paper, let's go this way. Yeah. It might help to draw a picture, get the scenario, cannon, how, blast a cannonball, then there's something about like that. Right? Ooh, it has some height, has some velocities, and hey, could you break the velocities into components? Like the initial blast velocity, you could say, what is v sub x and what is v naught y, right? That could get sorry, right? And how do you guys draw some graphs? Now the graphs I want to help you guys out with a bit here are the velocity graphs. So let's say, what is vertical component of velocity? That's v sub y in meters per second as a function of time ticking along in seconds. Okay. And then later on, we're going to do what is the horizontal component of velocity. It could also be in meters per second as a function of how much time is ticking in seconds. So we'll take a look at those. Okay. Oh, and I know I said 30 degrees. The angle doesn't really matter. I'm just looking for graph shapes. Right? I have a really similar looking pair of posters. You guys remember this pair of posters right here? Pair of posters, right? Ooh, this looks pretty much that scenario in slightly different angle, but same looking graphs, I bet. Right? So if you're ever not sure what the graph shape should look like, you can figure it out by plotting a bunch of points. I mean, isn't that what we've been doing for the labs? Right? Like your guys' car and incline lab, it's just we plot a bunch of points and said, hey, stand back, kind of what shape does that make? You could construct it like that. So vertical component of velocity versus time. Let's get it straight off this paper. We'll use the 37-degree angle and the 50 meter per second blast speed. Okay? So guys, leaving the cannon, how fast was the initial vertical component of velocity? 30 meters per second. Okay. Now let's go 1, 2, 3, 4, 5, 6 seconds. So I'll throw 6 seconds on the board. Let's go 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. Okay. And it looks like at time 0, it was leaving the cannon going strictly up at 30 meters per second. Bam, there's a point on the board. Is that true? Okay. How about after 1 second? Ooh, is it slowing down vertically? Slow down how much? By 10 meters per second. During that second, because gravity's pulling down 10 meters per second from 30 down to 20. Can you guys plot that point? After 1 second, now it's going down at, still moving upward, but at a slower rate. Right? And then 1 second later, it's now it's slowed down to how fast vertically? Right? You guys see it? So now we're down to this fast, meters per second vertically. Okay. 1 second later. Ooh, right here, guys, this ball right here is moving how fast vertically? 0. 0, right? So if you had equations and you said, oh, what's the velocity there? Careful, is it a horizontal or a vertical type equation? Because if it's vertical, it's 0 velocity vertical at the top. Right? That could be that point right there. Right? Then 1 second later, now it's coming down. Now it's picking up speed, but in the down direction, which that could be negative. Right? 10, 20, 30. That go like boink, 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 or something like that. Right? Now, of course, for your quiz answer, you're not just going to plot a bunch of points. Do you guys think you could make so? I wonder what graph shape that is. What graph shape is that? Right? I might refer to it as a curve, but I think all these velocity versus time graphs, they look like some version of a straight line. Actually, here, I'll go ahead and because there's a little bit more I want to point to in this. Right? But let's do a little review here. There's some other questions I could have asked. Right? Like this, guys. What is the slope of this graph equal to? Down 10 over 1, is that 10 meters per second squared negative? That sounds like gravity field for Earth. Right? And look, it's the same slope everywhere, whether it's moving up or moving down. Right here's moving up the first 3 seconds. Here's moving down the next 3 seconds. Right? But it's always accelerating down because gravity's always pulling down. Right? Guys, what about this? I can hatch in a triangle right here. That is a triangle shape, isn't it? What does the area of that triangle represent? Distance. Right. How about maximum height? Maximum height. Okay. And then after that, do I get a negative triangle? Okay. And if you add up the two triangles together, this positive triangle and this negative triangle, what number does that equal? 0. So 0 vertical displacement from here to here. That is also true, isn't it? It starts at ground level and ends at ground level. Is that true? Right. Now you don't have to do all that on your quiz, but just a little review there. All true. Right. Horizontal component of velocity versus time. So now we're looking horizontally. Let's go back to this. Okay, so here's the basic scenario. Okay. So leaving the cannon POW and then break into components. Here's how fast it's going across the field. Right. Then 1 second later, is it speeding up, slow down, or is it the same speed horizontally? Same. How about 1 second later? Same. How about at the very top? Now it's all horizontal. But look, it's the same as before. Okay, guys, it's the same all the way across, isn't it? Air drag, if there is any, would be negligible, so we're just ignoring that. Gravity doesn't pull horizontally. So here, if you plot the point, 1, 2, 3, 4, 5, 6 seconds. Let's see, it was going this fast horizontally. Then 1 second later, it's going this fast horizontally. Then this fast horizontally. This fast. This fast. This fast. Can you guys 3, 4, 5, 6, can you guys make a graph out of that? You guys think? Can you figure that out? Make a graph out of that? All right. Now, since we got a little extra time here, let's do the conceptual version right here. Right. Again, that's not all 3 graphs, but that's a couple of them. Conceptual has a different scenario. I said a cannon blasts a cannonball horizontally from the top edge of a cliff. That sounds like your guys' lab a few days back. You guys remember taking those launchers outside? Put a little launcher up here, aim it horizontally, and pow. And then ball goes, land somewhere out there. Right? So here's the conceptual physics scenario. You're getting like this. Okay? I have some of the same 3 type graphs, and I'll do 2 of them with you guys here. Okay? So let's do vertical and then horizontal component of velocity. The other question was, how far is the ball fallen versus time? Okay? So the more time that passes, the further distance it will have fallen. I give them 1 point, so 0, 0. So at time 0, it hasn't fallen anywhere yet, so they get that point. But let's move on to the velocity type graphs. So what's vertical component of velocity, say meters per second could be, as a function of time, say in seconds. And then horizontal component of velocity, also be meters per second, as a function of time in seconds. So there's a setup. Okay. So what these graphs look like? So 1, 2, 3 seconds, maybe. Because maybe we got like a 45-meter tall cliff. Right? It takes 3 seconds to hit the ground. So right when the cannonball is leaving the cannon barrel, How fast is it moving vertically? How fast vertically? Is it moving up or down at all? No. So at time 0, it has 0 vertical component of velocity. True, right? How about after 1 second? Is it moving down some velocity? How fast strictly down after 1 second? Aha, picked up to 10 meters per second during that 1 second. Okay. 2 seconds, 3 seconds. Okay. After 2 seconds, how fast vertically? Oh, actually, I kind of got that right here. Right here, here it is. So 0 meters per second vertically, then 10 meters per second vertically, 20 meters per second, 30 meters per second. Isn't picking up 10 meters per second, because that would be Earth. So 2, 20, 3, 30, right? Of course, I'm not looking for points. I'm looking for like some kind of graph curve, right? What shape is that? Right. Horizontal component of velocity. Again, I got that right here. Suppose you blast it this fast. Right? After 1 second, now it's moving this fast horizontally. After another second, it's moving this fast horizontally. After another second, it's moving this. You guys see? Boink, 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 boink. All you have to do is plot that. So see, at time 0, 1, 2, 3, right? It was moving this fast horizontally. Then after 1 second, it was moving that fast horizontally. Then after another second, that fast horizontally. Then after another second, that fast horizontally. You guys think you could connect the dots, make a graph out of that? Okay. And that's for my conceptual students. All right, you guys ready for Kahoot? It's Kahoot time. Let's switch over to Kahoot. Oh yeah, you guys are on, ready to go. The pen is on the board right here. You're not quite in yet. All right. Of course, these are conceptual questions related to projectile. Ooh, I wonder if maybe you're gonna see some quiz answers here in a few minutes. Quiz answers. I like pulling quiz questions off these Kahoots too. A vector, for example, acceleration, is a quantity that has both what and what. Yeah, magnitude and direction. Okay, so magnitude is like the number you can put in your calculator, but also a unit, right? So for example, how about gravity field, which is a type of acceleration? Could you say 10 meters per second squared? That's a magnitude, 10 meters per second squared, right? But also importantly, there's a direction. Now, a lot of times the direction is implied, like, okay, well, gravity only ever pulls straight down, right? But that would be important because gravity does not act horizontally; it only pulls vertically, okay, something like that. Okay. How about displacement? Guys, horizontal displacement, vertical displacement. Does that sound like a vector value? Like if you go to the right 5 meters, that could be a vector. How about velocity? Do you think velocities are also vector values? Got like 20 meters per second horizontally, 20 meters per second vertically. That's vectors. Okay. So vectors is not just how much, which is magnitude, but also a direction. Guys, if it's not a vector quantity, then it's called a what kind of quantity? Starts with an S. Like a scalar. Right? Talking a little bit about scalars, right? Which means it would maybe have a magnitude, but not a direction. There are, I think, 2 quantities we've talked about so far in this class that do not have a spatial direction. Because what's an example of something that does not have a spatial direction? Time. Time's a good example, right? And another example could be mass. Masses could also not have a spatial direction. All right. Points on the board. A scalar, for example, mass, is a quantity that has only a magnitude. Right? So it could be 5 kilograms, could be 5 seconds, right? But there's no spatial direction. So it's not like up or down or to the right. Right? So there's no spatial direction, right, for scalar quantities. All right, so what is vectors? What is scalars? All right, we got Jonathan, Zach, Luciana, Elise, Peyton. Suppose a plane can fly 100 kilometer per hour relative to surrounding air. It gets a boost from a 60 kilometer per hour tailwind. Now, what is its ground speed? How fast will it hit the ground? All right, all right. Looks like a lot of you guys caught this. Do you guys remember back last Friday? I left you guys with some videos with the substitute. This was one of the Paul Hewitt videos. So if you caught that, I want to draw this one out anyway. So say we got a plane. It's flying straight north at 100 kilometers per hour, straight north. Zoom. Right? Now that's how fast its engines can push against the surrounding air. Now if the air is not moving, that would also be its ground speed. Oh yeah, okay. They were on Google Classroom though, right? Google Classroom, right? What did you guys do on? Right. Okay. Well, they're all there. Back on Friday. I left you guys some videos and yeah, go take a peek at those. They talk about vectors, right? Right here, but we'll do a little review today, right? Now, guys, what if the air is also blowing the same direction? We got a wind. Notice I connected these vectors. It's called tip to tail. That's in some of those Friday videos too from a week ago. It's called tip to tail vector connection. So I'm adding these vectors geometrically. Let's throw on a number, 60 kilometers per hour. Right? Now, if you go from the tail of the first vector to the tip of the last vector, get something called the, does anybody know what type vector this is called? If you put it all together, it starts with an R. It's called the resultant vector. And put the numbers together, would that be 160 kilometers per hour? Now that's the plane speed relative to the ground. So here's the plane relative to the air. Here's the air relative to the ground. Put it all together, you get the plane relative to the ground. Now if there's some guy with a radar gun down on the ground pointing up at the plane, goes, zoom, it's breathing this fast. Ah, all right, you guys got that? All right, okay, so that's in one dimension, but hey, I wonder if there's maybe a two-dimensional version of that coming up later. Yeah. Got Hunter, Zach, Luciana, Elise, stay tuned. What is the resultant of 3-unit and 4-unit vector at right angles to each other? Right angles. You guys ever heard of a, here, I'm gonna draw this up. Okay. Let's say you're going camping. We got to pitch a tent right here. And I'm gonna walk into the woods. I'm gonna go 3 kilometers to the east. All right. And I'm gonna turn and go 4 kilometers straight north. 4 kilometers. Right. And then and then there's another campsite up here. So I'll pitch a little tent. Right. Right. And then I'm calling back to my home base. Maybe I got some friends back over here. They're saying, hey, how far away do you think you are as the crow flies? Whatever sound a crow makes. Guys, what distance would that be right there? 5 kilometers? How'd you know that? It's a 3, 4, 5 right triangle, which comes from Pythagorean theorem. Is that true? Got a little right angle right here. 3 squared plus 4 squared, 9 plus 16 is 25 square root. Yeah, it's 5 kilometers as the crow flies. You guys see how I added these displacement vectors? These are displacement vectors, aren't they? I added them together tip to tail right here. Actually, this 5 kilometers is, it's called the resultant. Isn't that the resultant vector right there? Wait, there's more. There's more. What angle is this right here? Inverse tan, 4 on 3 kilometers. It's like 53 degrees, right? Or if you like, this is 53 degrees. 53 degrees. How about this angle right here? Which is this angle right here? 37 degrees. So I could say, yeah, I'm 5 kilometers away, but to turn that into a vector, I want to say 37 degrees east of north. Because direction. Got 10 points. Oh, all right. Hunter and Elise taking the lead. A plane flying into a headwind loses ground speed, with the tailwind gains ground speed. What about a 90-degree crosswind? The wind's blowing straight to the side. Is the plane overall going faster or slower? One winner. Or maybe I should give you guys more time with that. That one takes a little thinking, but I can draw this out. Show it to you guys. Let's go back to the plane. So back to plane. It's plane time. We're flying. And say we're going, 40 kilometers per hour. I say, just flying straight north at 40 kilometers per hour. Now, if there's no wind, then that's also the plane relative to the ground. So plane relative to air or relative to the ground, it's all the same thing, just 40 kilometers per hour. But what if now there's a crosswind and the entire air mass is moving to the east at the same time? That's what wind is. Okay? I'm gonna put in a wind vector tip to tail with the plane vector. Let's say the wind's blowing at like 30 kilometers per hour. Is that right? So here's the plane relative to the air. Here's the air relative to the ground. I wonder what is the plane doing relative to the ground? Now, even though the plane's pointed north, it actually moves which way? Northeast. Aha. Right. And also shadow across the ground is following that path too. Suppose there's some guy on the ground, points a radar gun right up, straight at the plane. How fast is that radar gun reading? 50 kilometers per hour, right? Because is the Pythagorean theorem all over again? 30 squared plus 40 squared is 2,500 square root 50 kilometers per hour, right? And let's throw a direction in here, because what angle is this right here? 37 degrees, east to north. There you go. Now you got a magnitude and a direction. That's a vector. All right, ghost winner. A ball is thrown into the air at some angle. At the top of the ball's path, the velocity is entirely horizontal. I show that right here. You guys remember this pair of posters? I throw the ball into the air at some angle, and at the very top of the path, it's only moving horizontally. Okay? If you set up an equation and let vertical component of velocity go to 0, that would also mark the top. You could solve for things like how much time to get there, or ultimately what is the maximum height you could do. You answer those type questions too. Okay. All right. I go, Alexander, Zach, Elise, Luciana, Hunter. Ball thrown into the air at some angle. In the first second, it moves 5 meters horizontally. How far horizontally in the next second? All right. 5 meters again. Here, just real fast, in case anybody's watching this video at home saying, where? Is, constant horizontal component of velocity. Right? So if it moved 5 meters in 1 second, then it's always moving 5 meters horizontally every second. All right, all good, all good. We got Alexandra, Luciana, Zach, Elise, Hunter. Projectile maintains its horizontal component of speed because it is not acted on by any horizontal. There are not any horizontal forces. Guys, throw a ball in some air, at some speed into the air. It's going to go into a parabola type shape. Is there any force acting on it? Yeah. What force? Yeah, gravitational force, its own weight, right? Which we're going to start talking about next week is like what causes accelerations or would be forces, right? But that's vertical. Right? And we've been ignoring air drag. We usually do in this class, ignore air drag. In which case, there would be nothing left to act on it horizontally, right? Gravity doesn't pull horizontally. Gravity only pulls vertically. Yeah, no horizontal forces. So it's just constant velocity horizontally. We got Alexander on fire. Peyton, Hunter, Elise, Zach. What part of a path does a projectile have minimum speed? Yep, very top, very top. Okay, so you just point that real fast over here. Oh, it's not gonna go. Okay, so it's gonna slow down a little bit on the way up, and it's gonna speed up a bit on the way down. And yeah, minimum speed would be at the very top because yeah, here right? It's got all the same horizontal component, but the vertical goes to 0 at the top. Then yeah, Pythagorean theorem. Yeah, minimum speed at the top. All right, Luciana, Hunter, Peyton, Elise, Zach. Cannon fires cannonball horizontally off a cliff at 30 meters per second. How far horizontally will the cannonball move in 1 second? Aha, 30 meters. Right, so this is all horizontal, all horizontal. Right? So if you blast it horizontal at some speed, then that is its horizontal component of velocity. Right? It's always going that far every second. All right, Elise, back to the top. It's easier to hit a home run in Denver, Colorado than in Miami, Florida. True. Why? Ah, yeah, you guys got it. Yeah. Thin atmosphere, less air drag, which of course in this class we normally just ignore anyway. Right? But if you did consider it, that is true. Right. The air drag's going to slow down the ball a little bit, maybe enough to prevent a home run, possibly. Yeah. Yeah. It's easier. You guys ever been up in the mountains, up Denver, Colorado, maybe? Yeah. Yeah. You could tell the air is thinner. Right? You try to run around and get winded real fast. Ooh, yeah. Yeah. It's easier to hit a home run up there. There's not as much air drag. Ziriana on fire. Luciana, Zach, Elise, Peyton. In the absence of air resistance, the optimal angle to throw a ball the furthest distance is how many degrees to the horizontal? Ooh, nice, nice. Yeah, so why is it 45 degrees? Here, this one I want to draw out, make a case for you guys here. It's going to be a 45-degree angle. Okay, so let's draw this story. Say we're down here on the ground. I got this launcher, this projectile launcher, and I can change the angle. So 0 degrees would be straight horizontal, then 10 degrees, 20, 30, 40, 50, 60, 70, 80, 90, and then 90 degrees to the horizontal would be straight up top. Okay. Okay. Then I can start launching this thing. So it's 0 degrees. Now, if you're truly at ground level and launch at 0 degrees, like pretty much go nowhere. Okay. Then 10 degrees. Ooh, now it went somewhere. 20 degrees. Ooh, 30 degrees, 40 degrees. Right. How about 45 degrees? A little further. Right. 50 degrees. 60 degrees. 70 degrees. 80 degrees. 90 degrees. Clunk. I've gone over here. Okay. So let's throw a horizontal displacement, like the range on that axis. It could be. Okay. Let's make a graph out of it, and it'll be kind of tiny because I want to make a larger type graph right here. So on the horizontal axis, let's see the angle, say some number of degrees, goes 0 to 90. 10, 20, 30, 40, 50, 60, 70, 80, 90, 80, 20, 40, 50. All right. And then on the vertical axis, let's do how far the range in meters with that. So I saw when I aim it straight horizontal, like ground level, it didn't really go anywhere. So like 0, 0 is pretty much a point. Okay. Also, if I aim it straight up, just comes straight down and kind of lands where it started, which is also 0 range. So those 2 points could be on the graph. Wouldn't that be true? Okay. And then everything in the middle. So at 10 degrees, it was like, pow, ooh, when you get distance, 20 degrees, ooh, a bit further. But slow down a little bit, 30, 40, 45, 50, 60, 70, 80, and then 90. It's like there. If you put it all together, get a curve looks about like this, somewhere thereabouts. Right? Now, guys, really tricky question. Does anybody know what shape this would be? What part of shape it? What shape is that? It turns out it's actually not a parabola. Right? The full equation is right here. It's part of a sine curve. You guys know a sine curve looks like that S-looking curve, goes wow, 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 right? Like a Dr. Seuss roller coaster. Right? So here's the equation: x equals blast speed squared on gravity times sine of the double angle. Right? So in 90 degrees, let's try this point, guys. What is 2 times 90 degrees? Is that 180 degrees? What is sine of 180 degrees? 0. Ah, so at least I know this point's true. Right, something like that. Right, like that. Now why does it peak at supposedly this should be a 45-degree angle. Bing, like 45 degree, like this optimal angle. These are all degrees, right? Degrees. Okay. So I don't know if you guys caught this, but hey, guys, go take a peek at Google Classroom sometime. Of course, watch all those last Friday videos if you hadn't watched those yet. It tells you some stuff about how to add vectors together. But I also threw a bonus video sometime this week up there that I recorded a few years back. It's about 15 minutes long. It walks you guys through a proof. It shows why the optimal angle for the furthest distance happens to be exactly 45 degrees. Right? Takes a little bit of calculus. So if you think you're going to take some calculus someday, yeah, there's a bonus video on Google Classroom. And I'll show you guys how that works too. So you'll be, oh, okay, I see it. Right. Anything you're optimizing is usually a calculus type question. Go back to points. You got Alexander, Luciana, Zach, Elise, Peyton. Question 13. Cannonball launched 30 meters per second over a flat terrain. In the absence of air resistance, it will land with the speed of, slow down on the way up, speeding up on the way down. Yeah, there you go, 30 meters per second. You guys probably see by symmetry, it'd be equal speeds at equal heights. So it slows down on the way up, speeds up on the way down. Yeah, crash lands the same speed it was launched. All right, let's sports. Projectile launched horizontally, hits the ground in 1 second. What if it had been launched at a faster speed? Now what's the hang time? Ooh, should say the same. Here, draw this out too. You guys remember we took those launchers out a few days ago? Let's go back to that balcony. Okay, so here's the balcony. I'm going to say the balcony height is, let's call it 5 meters. It's pretty close to that. I'm just going to round it to 5 meters. Okay? We'll take those launchers, launch it. And let's say you guys have those bouncy balls. You guys have any bouncy balls that are like rolling off the edge? Like, fall straight down pretty much. Okay? Guys, how much time does it take to fall 5 meters? Is it 1 second? Right? So, or how about the other way around? How far does anything fall in 1 second? It would be 1/2 GT squared. That's like, oh, that's college. It's college equation. Where's that 5 meters? Right? 1/2 times 10 times 1 squared. 5 meters. Okay. So 1 second falls 5 meters. So 5 meters, 1 second. Okay. Now, what if you guys had different settings on those launchers? You guys had a slow, medium, and a fast setting. So how about slow setting? Pow. Lands there. Medium setting. Pow. That's it. Fast setting. Boom. It lands right there. Oh, suppose you launch them all at the same time. Guys, which ball hits the ground first? Or do they all tie? They all tie? They all take 1 second to fall 5 meters. It doesn't matter how fast they're going horizontally. Okay? Actually, what I said, I'm going to amend a little bit in an upcoming question. I forget how much upcoming, but right. But for now, what I've been telling you guys is it doesn't matter how fast it's going horizontally. They'll fall same distance in the same time. So it's basically true, right? Oh, Luciana moving up. Peyton's still in the lead. Object is thrown horizontally 30 meters per second off the top of a cliff. What is its acceleration in free fall? 10 meters per second squared downward. It doesn't matter what its sideways velocity, it doesn't matter what its velocity is at all. You could throw it up to the side at a 33-degree angle. It's always accelerating down 10 meters per second squared in free fall. Oh, yeah, on Earth. Lots of points. Luciana still on fire. Peyton still in the lead. Neglecting air drag. At what point is acceleration greatest for a ball thrown straight up vertically? Acceleration. Yeah, same everywhere. So you throw a ball straight up. It's moving really fast straight up. Now, as soon as it leaves your hand, it's in free fall. It's moving upward, has upward velocity, but downward acceleration. How much is it accelerating down? 10 meters per second squared. Right? Suppose it's been rising for a little bit. It's slowing down, still moving up. Is it still accelerating down 10 meters per second squared? What about at the very top? At the very top of its path, it's accelerating how much? Huh? Guys, very top of its path, it has 0 velocity, but how much acceleration? 10 meters per second squared down, right? And then it falls down faster, but it's always accelerating 10 meters per second squared down, right? So the velocity is always changing, the direction's changing, but the acceleration is the same. It's just Earth gravity field. I got Alexander, Zach, Elise, Luciana, still on fire. Peyton in the lead. Suppose you can jump 1 meter vertically. Now, what if you're on a skateboard moving 15 meters per second to the right? Now you can jump how high? Is vertical motion and horizontal motion completely independent? Look at you guys. All right. Okay. Hey guys, what if you're standing on a boxcar of a train? Can you still only jump 1 meter up? 1 meter. There you go. You guys getting this. All right. Here we go. In orbit, a satellite such as the space station. We haven't talked about it yet. If you guys get this. Satellite such as the space shuttle. Ooh, nice. Yeah. Simply a projectile falling around the curvature of the planet. We'll talk about this in a few weeks. We'll talk about orbits and how do orbits work. You guys ever seen a satellite go by? Right? If you watch the sky, sometimes you see one. Right? Suppose like International Space Station. It's about 400 kilometers up thereabouts. Right? It's called low Earth orbit. Now up there, about 400 kilometers up, the gravity field is actually not much different than down here at the surface. It's a little bit weaker, but not much. It's about 90%, about 90% the strength. Right? So yeah, there's still Earth, there's still plenty of Earth gravity, and so it is accelerating. Now the key is that it's moving so fast to the side, it's actually falling around the curvature of the Earth. You guys remember a few minutes ago, I said this question was coming up. It's like, oh, it doesn't matter how fast you blast a cannonball to the right, horizontally. If you blast, if you drop a cannonball off a cliff or blast it slow or medium or fast to the side, all those cannonballs hit the ground at the same time. Well, that's it's only true kind of until you start to consider the curvature of the Earth, right? And if you get going fast enough, the speed for Earth ends up being about 8,000 meters per second. You're actually falling around the curvature of the Earth and hence you go into orbit. Right? Hey, guys, what about this? Again, this is a question for a few weeks from now, but what if you found a race car on Earth? It has big old rocket engines on it, ready to go. And you hit the gas pedal and whoom, now you're going at like 8,000 meters per second. You're just watching the speedometer, like 8,000 meters per second. You would actually feel just like the astronauts in the International Space Station. You'd feel identical. They look like they're floating around gravity free. They're actually falling around the curvature of the Earth. That's how it's working. All right. Got Alexander, Elise, Zach, Luciana, still on fire. Peyton, still in the lead. A ball thrown straight up at 20 meters per second will return to the ground with a speed of 20, 10, 0, 10, 20. Ah, all right, so you guys get it? Slows down on the way up, speeds up on the way down. So same speed, opposite direction. There you go. All right. I think we're going in for the win here. We got Alexander, Zach, Elise, Luciana, Peyton, going for the gold. A cannon with barrel velocity, 120 meters per second, launches a ball horizontally from a cliff top. How far will the ball fall in 3 seconds? How far will the ball fall? 3 seconds. Ooh. Yeah, keep us in suspense here. Actually, you know what? I have you even better here. Right, guys, you blast a ball horizontally and you drop the ball at the same time. So we're back to flat ground. I'm ignoring the curvature of the earth. Right? Guys, do you have the same vertical motion? Do they fall the same distance in 3 seconds? I think they do. And what is that distance it falls? 45 meters? Is that the college equation? H equals 1/2 gt squared. Notice I left off the v naught t because v naught vertically is 0. Right? Maybe it's moving to the side, but not vertically. This is all vertical. Right? Let's plug in 3 seconds. So we got 10 meters per second squared. 3 seconds square the second. Guess what's 3 squared? 9 times 5 is 45. It's about 45 meters. How'd you know that? College equation. 45 meters in 3 seconds. The answer is 45 meters. All right, let's flip back over. Let's see how you guys did. I wonder how many students got that right. We're about to find out. 3 winners. 3 winners. Are you guys good with the 45-meter drop in 3 seconds? Okay. All right. Whether you drop the ball or throw it to the side, that would be true. All right. To the podium with the bronze, Elise. With the silver, Luciana. And the gold, Peyton. Runners up, Zach and Alexander. All right. Nice job, guys. It's going to be a wrap on the week.